Welcome back to the second class on the kinematics of plane motion of rigid body. Now we have to make a difference in this class between the two-dimensional motion and the three-dimensional motion. As far as the two-dimensional, because in our overall kinematic study of the rigid body, we will be dealing with the two-dimensional motion studies of the rigid bodies, what we also call as the planar motion studies or plane motion, two-dimensional motion, that's what we also call as a plane motion. And the second type of motion that we have to study as well, which we call as a three-dimensional motion, which is out of plane motion or the motion in three directions. First and foremost is important for us to understand what do we mean by 2D. In order to make students understand what is two-dimensional motion or plane motion, I am assuming the motion of a duster on a blackboard. For example, we are having a duster on a blackboard. We have a duster. Let's suppose we have placed a duster on a blackboard like this. This is our duster, and I will write this as this is our duster D. As far as this duster is concerned, this duster is used for rubbing up the blackboard. Okay, and as far as the motion of this duster is concerned, the motion of this duster is observed by the teacher as well as observed by the students. Let's suppose we as students are observing the motion of this duster. What is happening to this duster when the duster is being used for rubbing the blackboard? Okay, so who is observing the motion of the duster? Students are observing. Students are themselves sitting in the classrooms. Students are on the ground. And let's suppose we as students treat this to be our x-axis and treat this to be our y-axis. And we say, let this to be the origin of our motion. This is the corner of the blackboard. We treat this to be the origin of the motion. And this origin, from this origin, we will be measuring the position coordinates of different points of this blackboard, of this duster. Okay. Now, so this frame of reference, we defined it by the zeta. This frame of reference is the frame of reference from which we'll be measuring the motion of the different points of this duster. So this is our frame of reference. Okay. Specify 2 points on this duster. Let's specify the point P. We call this as point P. And specify one more point. Call that as point Q. We have 2 points. We are specifying 2 points on the duster. Point P and point Q. Okay. So initially, before the motion starts, let's suppose the duster is placed on the blackboard in this position, in this way. Therefore, we can say initially before the motion starts, as far as point P is concerned, the radius vector of point P is this. This is the radius vector of point P. And as far as point Q is concerned, this is the radius vector of point Q. Okay. And we also draw the radius vector between point P and point Q. Let that radius vector be this. So what we are doing before the onset of the motion, before the motion starts, we are locating 2 points of the duster, and on these 2 points of the duster, we are writing their radius vectors, and these radius vectors are written from the point O. And O belongs to the frame of reference, A belongs to the ground frame of reference, J. Along x-axis, we define a unit vector along x-axis, we call that as I cap. And we define a unit vector along y-axis, and that we call as a j cap. So as far as I cap and j cap are concerned, these are our unit vectors along x and y axis. Now let's call this as, this is radius vector of point P. We call this as R OP. This is radius vector of point P drawn from point O. This is a radius vector drawn from point O to point Q. We write this as ROQ. And this is radius vector drawn from point P to point Q. We write this as RPQ. These are different radius vectors that we have drawn in order to understand the motion of this, duster. Now what will happen? This all is in our mind, okay, before the duster starts the motion. Now let's suppose the duster starts the motion. The teacher starts rubbing the teacher starts rubbing the blackboard. As the teacher starts rubbing the blackboard, initially he places this duster like this. Okay, so the duster will have some thickness. Okay, so the duster lies on the board. Okay, now as he gives some motion, he can give motion in any direction. Okay, so let's suppose the motion given to the duster in the next phase is the duster is now placed like this. Now let's suppose the duster is like this. It is like this. The duster is now like this because once he rubs the board, he is free enough to change the direction of the duster he wants. So look what has happened. So this is one of the positions that the duster can attain. So initially this point P here, now this point P has reached here. This point Q here, now this point Q has reached here. Okay, so now we will have different radii vectors drawn from point O with respect to the ground frame of reference to point P and point Q. In the same way, so the radius vector P and Q is now in this direction. This is the radius vector P and Q in this once it's being once it moves in this configuration, the radius vector from P to Q will be in this direction. In the same way, the duster can have a position like this. It is possible that the duster is here. It is possible that the duster is here. Okay, so duster is now here. This position, duster will also attain this position. So this is now point P, and this is our point Q. Okay, so this is point P. Point Q is our point Q is here. So radius vector from P to Q, radius vector from P to Q will be in this direction. Okay, so if you look, there are infinite number of positions possible that the duster can attain. And look at the radius vector from P to Q. The radius vector from P to Q is changing its direction every time the duster is giving the motion. Not only that, the radius vector P is changing, the radius vector Q is changing, the radius vector PQ is also changing. Okay, at least we can say, at least we can define one more parameter associated with the motion of the radius vector PQ. That is, initially the radius vector, when we started from P to Q, radius vector was in this direction. Okay, this was the direction of radius vector. That is, let me draw it a bit clear. The direction of PQ, radius vector PQ, was this was the direction of a radius vector. Let me draw it a bit clean. The direction of the radius vector PQ was, the direction of the radius vector was, let me draw it a bit clean. Let's suppose this is point Q, this is point Q, and the radius vector are, this is the radius, oh sorry, the radius vector is this, and this is my radius vector RPQ. Okay, this is radius vector RPQ. So at least we can say, if we draw an axis very clearly, if we draw an axis to parallel to the x-axis here, if we draw an axis parallel to the x-axis here, so it means we can at least say initially, before the setting up of the motion, RPQ, this RPQ vector was subtending some angle with respect to x-axis, because this axis is parallel to x-axis. Therefore, the angle that it initially had was this angle. This was the initial angle that RPQ was subtending. Let's call that as theta, and this theta will vary with time, as we will see it. So initially, before the start of the motion, the angle between PQ with the x-axis was theta t. Okay. Now, as the duster is giving motion, again, locate your x-axis. As we locate our x-axis by drawing an axis parallel to x-axis, the angle that RPQ is subtending with x-axis is also now theta. But this theta and this theta is different. Okay, you can usually see it. This theta and this theta is different. Okay, now see here what is happening. Again, locate your x-axis. As we locate our x-axis, what's happening to PQ? The PQ describes an angle, and this angle is again different. This angle is again different. Okay, So every time the duster is given motion, every time the duster is given motion on the blackboard, the radius vector between any 2 points is defining at different values of angle at different instants of time with respect to x-axis. So if this theta t is varying with time, we can say that as far as this theta t is varying with time, this theta t is changing its angles at different instants of time with respect to x-axis. And you know, the rate of change of angle theta t with respect to time, the rate of change of angle, that is d by dt of theta t, rate of change of this angle is what we call as the angular velocity. We call that as omega. So we say as far as this 2 points of the duster are concerned, the 2 points of the duster, that is p and q, the radius vector between p and q is also having some angular velocity. That angular velocity we represent by omega. So this is very important. Understanding this angular velocity vector is very important, because once you are locating 2 points on the duster and you see that the 2 points at different instants of time are subtending different angles with respect to x-axis, which gives us a hint that it is it has some sort of angular velocity, and we call that angular velocity as omega. Number one. Number two is, what is happening to point q? Point p and point q. At this instant of time, this point p is here, point q is here. After some values of time, point p is here, point q is here. So the coordinates of point p and point q are changing with time. The coordinates of point p and point q are changing with time. I'm again saying the coordinates of point p and point q are changing with time. And the coordinates of point p and point q that are changing are only the x and y coordinates. Here the coordinates of point p are, it will have some x value of x, we'll write this as x1 comma y1. And here the coordinates of point q will be x2 comma y2. Okay, now when the duster is at this position, the values of coordinates of point p will not be x1 y1, they will be different from x1 and y1. The coordinates of point q in this configuration will not be x2 y2, they will be different from x2 and y2. So it means, as far as the point p and point q is concerned, the point p and point q coordinates are every time changing as the duster is given motion on the blackboard. Since this motion, duster is restricted to its motion on the blackboard. The duster is not, we are assuming that the duster is not given motion, the duster is not removed from the blackboard. Okay, once if the duster is given motion away from the blackboard, if that is, if the duster is placed, if the duster is not now kept on the blackboard but it's moved away from the blackboard, okay, that is when the rubbing of the board is over. Okay, when the teacher finishes rubbing the board, then what he has to do, he has to take this duster away from the surface of the blackboard. At that time, one more coordinate of the, one more coordinate during that time, one more coordinate of the p and q will change, and that coordinate will essentially be, that coordinate will be the z coordinate. That is, z coordinate will come into picture, the z coordinate will come into picture when the duster is moved away from the blackboard. As long as the duster is on the blackboard, as long as the duster is on the blackboard, this duster has some thickness, it will have its, p will have some value of z, q will have some value of z, because these p's and q's are not strictly lying on the xy plane, because the duster has some thickness. Okay, so this point p will be away from xy plane, this point q will also be away from xy plane. So this point p will have some z value, this point q will also have some value of z. But as long as this duster is lying on the xy plane, it has two-dimensional motion. But as you move this duster away from the surface of the blackboard, the z coordinates for both point p and point q will change, then we will have, say, it will have the three-dimensional motion. So as far as the two-dimensional motion is concerned, in a two-dimensional motion, only the two coordinates of the motion are changing, only the two coordinates of the particles of a rigid body are changing, while as the third coordinate remains constant. The third coordinate does not change. Okay, the third coordinate remains constant. But if you have all the three coordinates of the motion changing, then essentially the motion of a body is a three-dimensional motion. First of all, we'll be beginning with the two-dimensional motion. Then onwards, we'll begin with the the three-dimensional motion. But what's very important to understand, that when the body is having two-dimensional motion, the vector drawn between its any 2 points does have an additional velocity. That's what we call as the angular velocity, because As the body is having planar motion or two-dimensional motion, as the body is having two-dimensional motion or planar motion, and a vector drawn between any 2 points, its angle with respect to x-axis always keeps on changing. That's why it has angular velocity as well. Now we'll be deriving the relationship between points P and Q, which will be our next class. So we end up our class. Yeah, thank you.